Today, we're going to talk about exactly how wind turbines produce power. Can a few giant blades spinning slowly really generate usable electricity? The answer is yes. Wind turbines harness kinetic energy from natural wind through a series of energy conversions, turning invisible wind power into the electric energy we use daily. These massive blades are far from ordinary iron plates. A single blade can stretch over 80 meters, longer than a standard football pitch. Built to withstand millions of rotations, torrential rain, violent gales, and lightning strikes in extreme weather, engineers manufacture them with glass fiber and carbon fiber reinforced epoxy resin composite materials. This material keeps the blades lightweight enough to be driven easily by wind, while remaining robust, wear-resistant and fatigue-resistant, with highly refined technical specifications behind its design. Glass fiber reinforced composites dominate as the mainstream material for wind turbine blades, with roughly 20% of glass fiber products from enterprises such as China Jushi dedicated to wind blade production. However, glass fiber alone hits critical limitations once blade length exceeds 70 meters. Excessive self-weight causes severe bending deformation, which may even make blades collide with the tower. This is where carbon fiber becomes essential. Its tensile strength surpasses 3,500 megapascals, with a modulus around 5 times higher than glass fiber, yet roughly 30% lower in density. Hybrid reinforcement, combining carbon fiber and glass fiber, can reduce blade weight by 20 to 30%. Research from Delft University of Technology in the Netherlands confirms that replacing full glass fiber with carbon fiber for the beam structure of a 120-meter diameter turbine rotor cuts blade mass by approximately 40%. Moreover, carbon fiber composite blades boast double the stiffness of glass fiber alternatives, resulting in far less deformation under strong wind loads and much more stable operation. Carbon fiber is naturally conductive as well. Through specialized structural design, reliable earthing can be implemented to deliver effective lightning protection and prevent blade damage from thunderstrikes. Additionally, carbon fiber's vibration damping properties stop resonance between the blade's natural frequency and the tower's transient frequency, a phenomenon that would trigger catastrophic consequences if it occurs. Clearly, material selection alone determines whether a wind turbine can survive harsh operating conditions year-round. The largest modern offshore wind turbines feature blades over 120 meters long, with rotor diameters exceeding 240 meters and a swept area of more than 45,000 square meters, equivalent to 6.5 standard football fields. Standing beneath such a turbine, a human being feels tiny in comparison, yet the blades only rotate around 15 times per minute. At such low speeds, the generator cannot produce electricity normally, calling for a dramatic speed boost. Forcing the bulky, heavy blades to spin faster risks fracture. So how do engineers solve this dilemma? They install gearboxes, acting as high-speed acceleration gear systems for the turbines. Through internal gear meshing, the low rotational speed of 15 revolutions per minute from the blades is amplified roughly 100 times to over 500 revolutions per minute, enabling the generator to function properly. The gearbox stands as one of the most intricate mechanical cores of the entire turbine, adopting a hybrid transmission design, combining planetary gears and parallel shaft gears. Imagine it as multi-layer nested acceleration gear sets. The main shaft, driven by the blades, rotates at around 15 RPM into the gearbox, receiving initial acceleration from the first stage planetary gears, followed by continuous speed magnification via subsequent stages of parallel shaft gears, ultimately boosting the output shaft speed by 80 to over 100 times. During operation, the gearbox endures enormous torque shocks, as wind speed is never constant. Sudden gusts can send torque surging instantly. Every gear and bearing inside undergoes precise calculation and thermal treatment, paired with a 24-hour circulating lubrication system to eliminate dry friction damage under high-speed, heavy-load operation. Gearbox failures lead to far more than minor repairs. They often result in weeks of downtime, or even full cabin return to factory overhauls costing millions in losses. Hence, gearbox design and maintenance are paramount to turbine reliability. Still, the geared high-speed design is not the only solution. Three major technical routes have emerged alongside technological advancement in the industry. The first is the doubly fed high-speed transmission system we just covered. Equipped with a gearbox offering a transmission ratio between 80 and 1 in 75, it features mature technology and relatively low upfront costs. Yet the gearbox remains a vulnerable component, with high ongoing maintenance expenses. The second is the direct drive solution, which completely removes the gearbox. Blades directly drive an oversized low-speed permanent magnet generator several meters in diameter, packed with rare earth permanent magnets. Its multipole design generates 50 Hz alternating current directly, even at the low rotation speed of just over 10 revolutions per minute. Eliminating the gearbox removes the biggest source of mechanical failure and greatly improves reliability. But the trade-off is an extremely large, heavy generator paired with expensive rare earth permanent magnet materials. The third option is semi-direct drive, retaining only one or two stages of planetary gearboxes, with a low transmission ratio of 8 to 50, matched with a medium-speed permanent magnet generator. This design boasts a simpler structure than doubly fed systems while delivering a more compact, lightweight generator than full direct drive setups, making it the undisputed mainstream technical route for high-capacity offshore wind turbines today. Mingyang Smart Energy's semi-direct drive models integrate the main shaft, gearbox, and generator as a single unit, compressing the axial distance from the rotor to the generator to the minimum for ultra-compact, lightweight construction and outstanding power density, with single-unit capacity exceeding 16 megawatts now available. Each of the three routes carries distinct pros and cons, essentially representing different trade-offs between efficiency, cost, and reliability. Wind speed is inherently inconsistent, fluctuating constantly and causing variable blade rotational speeds that produce unstable power frequency. Power grids demand strictly precise frequency parameters. Even minor deviations can trigger blackouts and equipment damage. How do engineers resolve this issue? They equip doubly fed systems for generators, functioning as intelligent frequency stabilizers. When slow rotation causes low frequency, excess frequency interference is offset, ensuring stable, grid-compliant power output regardless of wind intensity. Though the name doubly fed induction generator sounds complex, its working principle is ingenious. A conventional induction generator features a fixed electromagnetic relationship between rotor and stator, meaning output frequency fluctuates alongside rotor speed. In contrast, the rotor of a doubly fed generator contains an extra set of coils connected via slip rings and carbon brushes to an AC-DC-AC converter, which acts as a smart frequency regulator. During low wind conditions when rotor speed sits below synchronous speed, the converter injects low-frequency alternating current into rotor windings to compensate for insufficient rotational velocity, keeping stator output firmly locked at 50 Hz. When strong wind pushes rotor speed above synchronous speed, excess electric power induced in rotor windings is recovered, converted, and fed into the grid by the converter, while maintaining steady 50 Hz current output from the stator. Within a reasonable speed fluctuation range, the doubly fed system adjusts the frequency and phase of rotor current in real time to stabilize output power to grid standards, serving as core technology for large-scale grid integration of wind power. Without it, widespread wind energy grid connection would be impossible. The doubly fed design holds an additional hidden advantage. It only processes 20 to 30% of slip power, allowing smaller, more cost-effective converters. Nevertheless, it has an inherent flaw. Slip rings and carbon brushes rely on physical-mechanical contact, suffering gradual wear that requires regular replacement. Corrosion worsens drastically in the high salt spray offshore environment, explaining why semi-direct drive and direct drive technologies gain growing popularity for offshore wind projects. Semi-direct drive configurations adopt medium-speed permanent magnet synchronous generators paired with full power converters. While converter costs rise accordingly, The removal of slip rings and brushes drastically enhances reliability, perfectly suited for offshore sites with exorbitant maintenance costs. Full power converters also deliver superior grid adaptability, enabling low-voltage ride-through and high-voltage ride-through capabilities to sustain stable operation amid grid voltage fluctuations, critical for overall power grid safety. A turbine cannot spin efficiently if its rotor faces away from the wind, and manual reorientation is entirely impractical. Engineers install wind detection hardware at the rear of the nacelle, an anemometer and wind vane acting as the turbine's eyes and nose to monitor wind direction and speed around the clock. Even minor directional offsets of just a few degrees send signals to the onboard computer, which activates the yaw system. Giant electric motors rotate the entire nacelle to keep blades perfectly facing the wind and maximize wind energy capture. The yaw system's braking mechanism is equally vital. Once the nacelle reaches the optimal angle, hydraulic clamping cylinders lock it securely in place to prevent unnecessary rotation caused by wind turbulence or unit vibration. Consider that a nacelle combined with blades can weigh hundreds of tons. Precisely rotating and locking such a massive assembly dozens of meters above ground demands extremely stringent standards for mechanical design and control precision. The yaw system also incorporates built-in cable twist protection. Cables run upward through the tower interior to the nacelle, and unidirectional continuous rotation would twist cables tight like a twisted rope until they snap. When the system records a preset number of rotational cycles, it automatically reverses direction to untwist the cables, a process known as cable unwinding. If unwinding fails, a final safety twist cable protector forces an emergency shutdown pending manual intervention to prevent severe accidents. The generator converts mechanical energy from high-speed rotation into electrical energy through electromagnetic induction. Simply put, the rotor spins inside the stator, cutting magnetic field lines to generate electric current naturally. Faster turbine rotation accelerates magnetic line cutting, yielding greater power output. However, electricity produced at this stage remains low voltage and unfit for direct residential supply. A transformer at the base of the tower steps up low voltage to above 33 kilovolts for long-distance transmission, drastically cutting energy loss during transport. Per Joule's law, line power loss is proportional to the square of electric current. Raising voltage reduces current accordingly, minimizing transmission waste and enabling efficient power delivery, dozens or even hundreds of kilometers to substations before distribution to households. The electricity powering your home air conditioner may well originate from wind turbines months earlier, passing through multiple voltage step-up and step-down processes before reaching your wall socket. Once blades rotate steadily, speed is amplified, frequency stabilized, and voltage elevated. Clean, eco-friendly wind energy supplies household appliances, including lights, air conditioners, and refrigerators. Consistent long-term turbine operation hinges on regular maintenance, much like scheduled servicing for automobiles. Lubrication systems and connecting components represent core maintenance priorities. Gearboxes and bearings within yaw mechanisms require constant, adequate lubrication. Lubrication system failure leads to dry gear friction, malfunctions, and even cabin fires. Connection bolts between blades and hubs, plus fasteners at tower splicing joints, demand routine inspection and retightening to prevent loosening or detachment from prolonged rotational vibration. Comprehensive troubleshooting during every maintenance cycle stops minor faults from escalating into catastrophic failures. Lubricating oil undergoes scheduled replacement alongside real-time monitoring of oil quality and temperature. Continuous rotation and vibration induce metal fatigue and gradual loosening of bolts. Neglected inspections for a single critical loose bolt can result in blade detachment or tower fracture under centrifugal force with devastating outcomes. Maintenance engineers use torque wrenches to retighten every bolt to specified torque values during routine servicing, meticulously eliminating potential hazards to guarantee safe turbine operation. Feel free to bookmark this video if the content feels information dense for later review. At this point, you may question whether such complex, high-maintenance wind turbines are economically worthwhile. The answer is an emphatic yes, supported by authoritative official statistics. Per the latest figures released by the National Energy Administration of China, China's cumulative installed wind power capacity hit 521 gigawatts by the end of 2024, ranking first globally for consecutive years. Annual national wind power generation reached 996.8 billion kilowatt hours in 2024, accounting for 10.1% of China's total electricity output. In other words, more than 1 out of every 10 kilowatt hours you consume comes from wind. A report released by the International Renewable Energy Agency in April 2026 states that global new renewable energy installed capacity reached an all-time high of 692 gigawatts in 2025, with wind power contributing 159 gigawatts, marking a 14% year-on-year increase. Wind and solar photovoltaic power together made up 96.8% of all newly added renewable energy capacity worldwide, meaning nearly all newly commissioned clean energy installations globally consist of wind and solar power. The International Energy Agency, IEA, forecasts that renewables and nuclear power will collectively supply 50% of global electricity generation by 2030, with wind power seeing exceptionally robust growth. Between 2025 and 2030, cumulative new onshore wind capacity is projected to rise 45% to 732 gigawatts, while new offshore wind installations will reach 140 gigawatts, doubling the figure from the preceding 5 years. These statistics reflect decades of accumulated progress in wind power technology and an irreversible global trend toward energy transition. Conventional onshore wind turbines only perform well in regions with steady wind resources, struggling in permanently windless zones or areas with erratic wind speeds, calling for alternative power generation solutions. Engineers have turned focus toward the vast ocean, positioning offshore wind power as the next trillion-yuan industrial track. Offshore winds are stronger and far more consistent than onshore winds, while offshore installations occupy no precious land resources. Data from the National Energy Administration and Global Wind Energy Council shows China's cumulative offshore wind installed capacity stood between 42 and 44 gigawatts as of June 2025, securing 6 consecutive years as the world's top market for new offshore wind additions. Guangdong Province's long-term technically exploitable offshore wind potential exceeds 100 gigawatts, equivalent to 10 Three Gorges hydropower stations. Yet offshore wind development poses challenges several times greater than onshore projects, including seawater corrosion, typhoon impacts, deep water foundation construction, and power transmission, each representing world-class engineering challenges. Chinese engineers are spearheading a technological revolution to overcome these obstacles. First comes turbine upscaling. The world's largest 26-megawatt offshore wind turbine has been successfully connected to the grid, boasting a rotor diameter exceeding 300 meters and a swept area equivalent to 7 football pitches. Its annual power output meets the electricity demand of tens of thousands of households. The hub sits at a height of 152 meters, with hundreds of sensors and LiDAR devices across the unit monitoring temperature, humidity, wind speed, and other parameters to digitally track operational status. An onboard intelligent control core dynamically adjusts blade angles and power output accordingly. Second, blade material upgrades are underway, with carbon fiber composites gradually replacing traditional full glass fiber materials. Carbon fiber is roughly 30% less dense, yet several times stronger than glass fiber, enabling ultra-long 100-plus meter blades that remain lightweight yet structurally robust. Mingyang Smart Energy has developed 118-meter carbon glass hybrid blades, adjusting carbon yarn and glass fiber ratios to achieve linear modulus variation, solving insufficient glass fiber modulus and high carbon fiber cost issues. Prototypes have completed verification and certification, ready for mass production. Times New Materials has achieved breakthroughs in core technologies including carbon fiber pultruted plates, glass fiber pultruded plates, and PET core materials, enabling low-cost, lightweight blade design. Floating offshore wind technology represents the cutting-edge frontier. Nearshore water depth allows fixed turbine foundations anchored directly to the seabed via pile driving, yet water depths exceeding 60 or even 100 meters in deep offshore waters make traditional fixed foundations prohibitively expensive. Engineers have developed floating platforms that support turbines like massive vessels secured to the seabed via anchor chains. The world's first complete 16-megawatt floating offshore wind power system has finished assembly, marking China's transition from a technology follower to a global leader in offshore wind power. The floating offshore wind market is projected to expand from approximately $477 million in 2025 at a compound annual growth rate exceeding 33% to $8.39 billion by 2035. Forming a rapidly expanding blue ocean industry. The UK government plans to install roughly 50 gigawatts of offshore wind capacity by 2030, including 5 gigawatts from innovative floating technology, set to create nearly 90 and direct and indirect jobs. No advanced oversized turbines deliver value without reliable maintenance, prompting the industry's full shift from periodic scheduled maintenance to predictive condition monitoring, equipping turbines with intelligent diagnostic systems. Vibration sensors, temperature sensors, and oil analyzers are deployed at key components including gearboxes, generators, and main bearings, supplemented by acoustic monitoring inside nacelles and external drone inspections to gather massive volumes of operational data. AI algorithms conduct deep learning analysis on this data to build unique health profiles for every turbine. The system delivers early warnings 14 to even 21 days in advance upon detecting abnormal vibration, temperature spikes, or rising metallic wear debris in lubricating oil, pinpointing upcoming bearing failure or loose bolts for maintenance teams. Dongfang Electric's Eagle Eye system achieves a fault warning accuracy rate above 95% using acoustic and visual algorithms, cutting unplanned downtime by over 30%. Sany Renewable Energy's drone inspection system covers a 10-square-kilometer wind farm per flight, paired with AI image recognition, delivering 98% accuracy for identifying blade cracks. The Fangchenggang Offshore Wind Project in Guangxi deploys intelligent inspection robots with 5G communication, boosting booster station operational efficiency by 40%. Longkan Smart Energy's Wind Power Brain platform integrates operational data from 232 wind turbines, adopting digital twin technology to map real-time equipment health status and reduce annual maintenance costs by over 5 million yuan. Goldwind's Smart Operation and Maintenance platform connects data from more than 7 wind turbines with 13 scenario-based algorithm models. These technological implementations are revolutionizing wind power maintenance, shifting from reactive breakdown repairs to proactive risk prevention and transforming human-led equipment supervision into data-driven management. Offshore wind maintenance faces a unique accessibility challenge. Offshore wind farms lie dozens to over 100 kilometers from shore, and conventional service vessels cannot sail during severe weather, leaving faulty turbines unattended for extended periods. Purpose-built offshore wind service operation vessels, SOVs, have emerged as the solution. The global fleet of professional offshore wind SOVs is expected to grow from 88 vessels in 2024 to 600 vessels by 2050. China's domestically developed 98.7-meter multipurpose service vessel, Fenghua, number 23 is operational, supporting deep-water operations 100 kilometers offshore, with a cruising range exceeding 10,000 nautical miles. Equipped with onboard accommodation, a helicopter landing pad, and heavy lifting cranes, it functions as a mobile offshore maintenance base. The widespread adoption of service vessels and unmanned technology will further lower the levelized cost of electricity, LCOE. For offshore wind power, already undercutting coal benchmark electricity prices as realized in 2025. Phase 1 of the Jinshan offshore wind farm in Shanghai fully fitted with 36 units of 8.5 megawatt turbines, stands as China's first competitive offshore wind project priced below coal benchmark tariffs, ushering offshore wind power fully into the grid parity era. Finally, we address a widely debated question. Is wind power genuinely environmentally friendly? Turbine operation generates certain noise. Rotating blades pose minor risks to bird life, and large wind farms alter local landscapes to some degree. Nevertheless, engineers have developed comprehensive solutions to mitigate these downsides. For noise reduction, modern turbines optimize blade airfoil profiles, limit tip speed, and install sound insulation inside nacelles to keep noise levels extremely low. For avian protection, many wind farms deploy bird radar monitoring systems that trigger automatic turbine shutdown or blade angle adjustment when detecting migrating bird flocks to minimize disturbance. Landscape concerns remain largely subjective aesthetic and planning issues, with numerous wind farms now popular industrial tourism attractions. Most critically, wind power's full life cycle carbon emissions amount to a tiny fraction of coal-fired power, releasing no sulfur dioxide, nitrogen oxides, or particulate pollutants. Its overwhelming environmental benefits far outweigh localized minor drawbacks, and ongoing technological advancement continues to shrink these adverse impacts further. What other clean energy solutions complement wind power? The world is aggressively scaling solar, photovoltaic, hydropower, nuclear, biomass, geothermal, and other renewable energy sources. Solar PV capacity expansion has even outpaced wind power, with global new solar installations reaching 511 gigawatts in 2025, representing a 27.2% year-on-year increase. Hydropower, the most mature renewable energy technology, boasts global installed capacity exceeding 200 gigawatts. Despite ongoing debate, nuclear power remains indispensable as baseload power within carbon neutrality roadmaps, while biomass and geothermal energy serve niche applications effectively. Wind power's unique strengths lie in its scalable deployment on land and at sea, widespread resource availability, mature technology, and continuously falling LCOE. IEA data confirms global new wind capacity maintained rapid growth in 2025, with China contributing nearly 3/4 of global new wind installations single-handedly. From massive onshore wind farms across northwest desert regions and rows of offshore wind turbines along southeast coastlines, to future deep-water floating wind arrays, these steel giants are reshaping the global energy landscape at unprecedented speed. Next time you spot those slowly spinning wind turbines on distant mountain ridges, recall the sophisticated engineering systems detailed in this video, alongside the persistent efforts of countless wind industry professionals maintaining these green power engines. Through scorching heat and bitter cold, wind has long symbolized freedom, and humanity has now mastered harnessing it to generate electricity that illuminates modern civilization sustainably. If this in-depth technical breakdown has given you brand new insight into these seemingly familiar yet highly sophisticated engineering marvels, leave a like to share this knowledge with more viewers. See you in our next video.